Alrighty, folks, let's go ahead and get started. So, um, thank you guys for joining me. This is one of our Manifold Frontier talks where we present research at the cutting edge of, well, just to double check before we get started, can you guys hear me properly? Um, let's
Yes, I,
see.
I can.
You can. Okay. Okay. Awesome. Okay, everybody gave thumbs up. Great. Okay, so welcome to Frontiers. This is our series on frontier topics, cutting edge research and development in various moonshot technologies, both within Manifold as well as outside of Manifold with our collaborators and partners. Oftentimes we host talks from guests, but this time we're proud to present our work on autonomous self-repair. Specifically, today I would like to present our work on stress sharing. It's a bio-inspired approach that we thought of for decentralized fault repair in modular spacecraft. This work was done with, of course, with myself, but also huge thanks to Yue, who is my close collaborator and our Manifold OS team member on this project, as well as my advisor, Xiaoshuai Mo, of course, who gives me his input and his feedback and his valuable advice on every research related thing that I do and more. So, without further ado, let's go ahead and get started. So, what do I mean by modular spacecraft? Okay, so the motivation for this project comes from the following. There is a powerful new class of robots called modular reconfigurable robots, which is coming into being very quickly. They have a variety of shapes and sizes. Some of them are cubes, like the Electrovoxels project from MIT. Some of them are spherical, like the snail bots from, I believe, ETH Zurich, but I'll have to double check that. Um, these modular reconfigurable robots possess the potential for tremendous adaptability, and they mark a significant departure from the prior way of doing things, which was to have a unibody robotic design. Okay, unibody robotic designs are, of course, more durable. They are easier to make, but they can't do stuff like this. Uh, Reconfiguring for the sake of uh, having new structural properties or reconfiguring for the sake of obstacle traversal, which I believe it will show now. Um, so this work is on another spherical robotic design, spherical modular robotic design that is very relevant for what we do in this project, what we're addressing in this project. And as you can see, this type of robotic body is very, very adaptable. You see it in a terrestrial application here. However, these types of robots seriously shine when it comes to in-space applications. And the reason for that is because there's microgravity. Or as I was recently corrected, there is weightlessness. Gravity is the same, you're just falling around the Earth, and the Earth is curving away from you as you fall. So the robots are under a weightless regime, in which case small actuation can affect great change. And so these sorts of modular robotic designs become much more viable. Okay, so I'm going to proceed here. What could these modular robotic systems provide us? What could they do that normal unibody systems cannot? Well, there are three powerful lifelike capabilities that exist in biological systems that we would love for these types of robots to have. So one of them, which you saw in the previous video, is morphogenesis, the ability to change from one shape to another depending on the situation, as called upon by the situation. Another one would be homeostatic capabilities. So let's say that one of the modules is damaged. Well, rather than the entire robot losing its function, the a robotic system with homeostatic capabilities could potentially reconfigure so that system function is restored. And finally, metabolism. So there have been some previous papers exploring some of these ideas, but what if modular robotic systems spit out the damaged module and take in a fresh new module and integrate it into their system, I guess for lack of a better word. These are all capabilities that biological organisms have, and they're all capabilities that could be immensely useful in long duration and autonomous modular robotic setups, especially in space, where intervention is very difficult and costly to do. Okay, so in this project specifically, we aimed to develop a homeostasis mechanism for a modular robotic system. Specifically, in the event of module failure, we aimed to develop a method to quickly and autonomously restore connectivity. This was one of the many objectives that we could have chosen, but we chose this one because it is applicable for the notion of connectivity is a very abstract notion. So this could be electrical connectivity, this could be communication connectivity, this could be structural integrity, but graph all of those sorts of various physical application specific attributes can be represented by the same underlying mathematical object, which would be a graph and the graph's connectivity. Okay, so there is some prior work, of course, not specifically in connectivity restoration in modular robotic systems, but there is relevant work in three fields. So one of them is, of course, connectivity restoration in networks, specifically wireless networks. This was the most informative sort of literature that we looked into. There are many distributed algorithms that restore graph connectivity after node failures in wireless networks. But restoring graph connectivity in a wireless network involves um, involves the changing of which node that you are targeting with your wireless transmission, not the physical motion um, of a robotic body, which is highly constrained. Specifically, in this case, there are fixed distance constraints that are required by modular robots that are ignored, or I shouldn't say ignored, but rather not considered in this field of wireless network connectivity restoration. But there's some very useful ideas there that we did leverage later on in this work. Another field that's highly relevant, of course, is modular robotic reconfiguration. So there are existing reconfiguration techniques for modular robotic systems, um, cubic systems or spherical systems. But these reconfiguration methods often rely on centralized planning. They use heuristic methods, path planning methods like A star or other similar heuristic-based centralized path planning methods. Um, the computational cost typically grows as the number of agents increases. But of course, if you have a large swarm modular system, you want the computational cost. You don't want to use a centralized high computational cost mechanism for rapid homeostatic equilibration, right? Rapid homeostatic repair. You want to have a system that scales that you want to have a system whose computational cost scales well with the number of agents in the system. And so uh, modular robotic reconfiguration literature as it currently exists, although it's a more general class of problem, it does not really apply to this homeostatic rapid response situation that we find ourselves in. And of course, the final area, which is very well studied in the field of autonomy and controls, is formation control. Formation control for satellites, formation control for drones. There are there's a lot of literature on formation control. But typically it relies on redundancy and fallback behaviors. There are many decentralized formation control mechanisms, but a modular robotic system is not exactly in a formation. It's a highly constrained sort of setup. And so moving from one formation to another in a pre-specified manner may not work. Your path may be blocked by other modules that exist in the system. So there's not much work that currently exists in connectivity restoration for modular robotic systems, and that's where we wanted to step in here. Okay, so we took a natural inspiration with this project. Why? Because we are talking about homeostasis for modular robotic systems that operate in a decentralized and rapid way. There already are modular robots in your body that restore connectivity in decentralized ways. Those would be your cells. And so, if we wanted to endow machines with lifelike capabilities, why don't we imitate life? Why don't we pull from the algorithms of life? And so that's what we tried to do in this project. Um, biological wound healing typically involves a stress sharing mechanism where damaged cells or cells near damaged cells propagate a stress signal, and other cells respond and move towards that wound, the wound site. And so we wanted to imitate that mechanism here, and that's the stress sharing algorithm that we developed for this project. And you can see in the bottom portion of this figure, if damage destroys the connectivity of this modular robotic system, then by the end modules moving towards the source of damage, they're able to effectively bridge this gap and restore connectivity to the system. So just specifically a couple of details about this algorithm, since we have more time to go in depth um, in this talk. The algorithm breaks down into two portions. The first portion is the coagulation phase. So in the biological analog, when you have a wound, the first thing that your body does is it sends material, sends cells there to try to pack the wound, right, to try to stop the bleed. And so, analogously, the first phase of our algorithm is to propagate stress tokens, and then modules that receive those stress tokens head towards the site of the damage. And the way that they know which direction the damage is in is because as those stress tokens, those damage tokens, are propagated along, the relative vector for the neighbor that each token was received from is added, and that sum becomes a vector that is added to and is added through to, and through vector addition points towards the source of damage. And so that is why, upon receiving a token, the module that is able to move also receives the direction that it should move. So then it runs a local calculation. Can I move in that direction um, while doing fully legal moves and while not creating a new disconnection in the graph? If so, then it takes a pivot towards the damage source. And so this is akin to biological coagulation, where the modules crowd around the damaged site and thereby restore the connectivity in the graph. But this is only half of the system, because if all of the modules move to coagulate around the wound site, then all structure in the modular system is lost. It would just become a sphere, right? It would just become a spherical ball of modules. Whatever it looked like before, it no longer will look like that. And so we have a second phase to the algorithm. Once the damage is repaired and the connectivity of the graph is restored, then the modules attempt to retrace the path that they took to try to reconstruct as much of the structure as it was before as they can. And the reason why they may not always be able to do this, because once the graph is coagulated, the damage module is still there. And so, of course, they can't just fully restore to how they were before, because then that would recreate the disconnection in the graph. So, in other words, the restructuring portion of our algorithm, the objective of that is for each module to try to go back to how they were before while not creating a new disconnection in the graph. And so it leaves behind another biological analog being scar tissue. The scar tissue being excess modules that are concentrated around the wound. But this is a natural consequence of trying to repair a fault in this manner. Okay, so that's kind of how our algorithm works. And um, we found some interesting results. So at first, these results were a little bit mildly discouraging. What we found is that as the number of modules increased, the full connectedness, the full repair of the system went down. And this was for both types of errors, or sorry, both types of damage that we tested. Randomized damage, where the random modules are damaged, and then localized damage, where a cluster of modules is damaged. So this simulates two different types of failure modes, one being if something were to suddenly go wrong, maybe because of radiation or something, with modules at random, and the other one maybe being a damage scenario where there's some kind of impact and it causes a localized destruction event. Those are the two types of damage scenarios that we tested. And what we found is that the full connectedness of the graph did decrease across these two error types and across these two damage types and across increasing numbers of modules being damaged. However, full reconnection may have gone down, but the percentage of modules that were put into the same graph at the end, or into the same component of the graph at the end, actually increased with the number of modules. Okay, what does this mean? So what this means is that while not every module was added to the same graph, the majority of modules, the vast majority of modules, in some of these cases, 98% of modules, were aggregated into one graph again. And so the partial repair of the structure improved. And when I say partial, I'm being a little bit conservative because 98% repair of the structure or 95% repair of the structure held constant and even improved as the size of the structure went up. So in other words, this mechanism, it's a simple greedy mechanism where modules go towards the source of the damage unless their motion would create a new disconnection. This alone, this simple sort of stress sharing mechanism alone, um, is able to scale well to up to 160 modules in our test. Um, as long as our objective, they were not able to achieve full reconnection, but they were able to achieve 98% reconnection, 95% reconnection. And those numbers improved as the number of modules increased. Okay, just a brief note about what is being shown in these graphs. The dashed lines are the localized faults, and the solid lines are the randomized faults. And you'll notice that the dashed lines are better in terms of the reconnection. And the reason for that is because, yes, in our testing localized faults, our algorithm was able to repair them much more effectively. It was able to reconnect the graph much more effectively than when the faults were fully randomized. One quick note here about these words tree and fully connected. How do you generate a random modular structure? We generated it in two ways. One of them was to make tree structures where every new module is only has one neighbor. And in that case, then you get these sort of large tree structures that have many, many leaf nodes, modules that are able to move freely. Um, Random damage really caused a lot of disconnections in that type of graph. However, there are many, many modules that can move, and therefore um, they do. And that's reflected in this bottom graph, but I'll get to that shortly. Fully connected graphs, basically every new module that is added such that it is neighbors with um, all other modules, as many other modules as it can be. And so that creates much more dense structures. Um, Solid cubes would be an example of that, or a rectangular prism would be like a fully connected structure. So in those cases, damage events actually cause fewer disconnections because there are many more redundant pathways, but there are far fewer modules that can move in those types of structures. And so we found that the algorithm performed worse in fully connected structures than it did in tree structures. So that's kind of the breakdown of these two graphs. And now what's happening on the bottom here is that the it's one thing to say that, after the repair phase, 98% of the structure is within the same graph component. That's fine, but your question should be, wait, after damage, um, how many graph structures were, or sorry, how many graph components were created by the damage event? And so that's kind of what this second plot is showing. It is showing how much repair, the shaded region is how much repair uh, actually occurred due to the algorithm. Because it would be easy if the damage event just caused uh, two graph components to form instead of one, and then one module motion reconnects them, and so they turn into one component again. That would be too easy. Or, I mean, that would be great, but that would just be one type of scenario. And what we want to know is how much repair is caused by this algorithm. So in the tree structures where random damage events caused many, many graph components to form, the repair was excellent. It did it would repair by 40%, 60%. It would aggregate modules into the same graph component. But in the fully connected case, damage was never that bad, meaning that damage events, localized or random, never created that many graph components. And so there wasn't much to repair. And that's kind of what you're seeing in these two charts. So the takeaway from this is that our algorithm, the stress sharing algorithm, works much more effectively in tree type graphs than it does in fully connected type graphs. And it works better with localized damage events than it does with randomized damage events. And what you see on the left is just a GIF that's been repeating, basically showing the method in action. So you see the coagulation happen and then reconnection of the graph. And it wouldn't be a swarm method if it didn't apply to large structures. So on the left, we have 50 modules, and on the right, we have 150 modules. And you can see that these are localized damage events. You can see that the reconnection occurs shortly. Those yellow pulses that you're seeing, those are modules deciding whether they can move or not. And so sometimes you see these yellow flashes because modules will receive a token, decide that they can't move, and propagate the token. And so those are these kinds of yellow flashes that you're seeing zip around the structure. In these two scenarios that you're seeing here, it just so happened that full reconnection happened. But like we saw in the previous charts, usually with these larger structures, 95%, 98% reconnection happened, not full reconnection. Um, but I'll talk more in a little bit about that quote unquote last mile, how to get that last mile. Okay, so just to recap what we've talked about so far, here's a brief video showing detailing the algorithm and also showing some more examples of it working. By the way, one more quick note here is that what you're seeing in these space simulated videos with these background stars, what you're seeing is a physically accurate simulation using PyBullet where angular momentum is conserved. And so the pivoting of modules causes the entire structure to pivot. There's a very slight angular momentum leakage because it's a numerical solver. Um, and so you see that like even though the modules stop pivoting, the spinning continues a little bit. That's a leftover because it ran on my laptop and that's um, that's just what you get when you run a numerical solver with fewer time steps or larger time steps. Okay, what we see here is the two types of faults, and it's reconnecting them. And then it attempts restructuring to try to recover as much of the prior structure as possible. And finally, in this last one, you see the same 50 module structure that we saw earlier. And all that we're saying here is that the method scales well with the number of modules in terms of its computational cost because it's decentralized. And these sorts of decentralized bio-inspired methods, they hold promise for large-scale modular space systems to adapt in the face of damage, and potentially also modular systems here on Earth as well. Okay, so what's next? So now that this project we've released the stress sharing algorithm, this preprint on arXiv. We're moving on to a more ambitious project, which is the full rapid reconfiguration of modular structures, not just in response to damage, but from any shape, any initial shape that you want to any terminal shape that you want. And we're exploring a variety of methods here. Some of them are using optimal transport methodologies. Some of them are using mean field game formulations. We're really sort of in the exploration phase here. We're trying a bunch of different stuff, but we're quite excited about this next direction. You see here that we're considering spheres in these GIFs, but ultimately we want to generalize to any polyhedral shaped modular structure. So cubes, tetrahedra, any of these systems because the cubic systems can pivot and the spherical systems roll and they all move in sort of different geometric ways. We want to find a general method that can apply to all of them to quickly and rapidly make any shape that you want. This is a step towards, an ultimate goal of programmable matter where you can arbitrarily generate structures. And that has applications in space, of course, but it also has applications here terrestrially. The space applications are top of mind though, and so I can think of there maybe if you want to increase your surface area with respect to the sun to generate more power, or maybe decrease your drag profile, or become a more lace-like structure so that you can be less expose less surface area to micrometeorites. What are some other examples? Maybe you want to change your radio characteristics, and so you form a modular antenna using these types of structures. So the possibilities are endless, and it is a difficult control problem because highly constrained and highly coupled. Um, and we're on it. So this is the next project. We're recruiting for this project now. I'll briefly talk about opportunities to get involved shortly. Okay. So guys, thank you for coming to this. Sorry. Thank you for coming to this Frontiers talk, and thanks for uh, sticking with us so far. We're very proud of this output. It's a very interesting research direction to try to take the natural modular robotic systems that are your cells and learn from them and um, try to apply that to space systems as well as potentially micro robotic systems. Um, Nanites, these sorts of modular robotic systems can come up in any domain. Um, we have more deep dive articles coming out now. So we just released one on our website newsletter about this project, as well as the preprint. And the links for those are in the description of this event, by the way, on Zoom. Um, Subscribe to our newsletter. We've got many more coming out later this year. And projects, like I mentioned, are recruiting. So if you go to manifoldrg.com/opportunities, you can see all the projects that are recruiting. Like I had mentioned, if you go there, you'll see that the rapid reconfiguration project is recruiting. We are looking for mathematical talent so that we can formulate and generalize across robotic embodiments. But along with the rapid reconfiguration project, um, very soon I will also be posting an extension for this project where we try to capture that last mile. So, like I mentioned before, this algorithm is a strictly sort of greedy algorithm in the sense that modules receive a stress token and then they move towards the source of stress. And as the structures get larger, that starts to leave out one or two modules somewhere on the distant edge of the graph. We want to get all of those. So the next extension of this project would be one, to fully reconnect by adding some additional biological mechanism. And the second thing would be to reconnect while maintaining some sort of constant topological constraint. Maybe you need to maintain some structural integrity by holding some kind of structure that's pre-specified, so like internal columns or something like that. Or maybe you need to maintain your a certain surface area exposure to the sun at a certain angle so that power generation is not compromised by reconfiguration. So considering constraints during the homeostatic um, reconfiguration would be a follow-up that we're going to do for this autonomous self-repair project. And so more on that is going to go up on manifoldrg.com/opportunities shortly, and we'll announce those. We're looking for technical collaborators in those areas. And yeah, we'd be stoked if you guys would apply, and I would love to talk to you guys about that further. You can, of course, watch recordings of this event and others at our YouTube channel. Um, Manifold Research on YouTube. We'll be posting this one on Monday. Um, and if you want to see future events, subscribe to our Luma calendar. We have a ton of events planned for the back half of 2026, um, including more talks like this one. Um, yeah, we have a lot more outputs coming out. So if you want to stay up to date with Manifold, check out the links below. We have an active Discord. Our GitHub is also public and active. And you can follow us on LinkedIn and Twitter. We post regularly. We post research content. Um, and we would love to talk to you and hear from you. So I'm going to leave this slide up, and now I would love to open it up to any questions that you guys may have. I saw a bunch of questions in the chat. I'm going to switch over to the meeting, and thank you guys so much for attending. Alrighty, let me just make sure everybody's able to unmute. Oh yeah, you guys are able to unmute. So let me briefly check through the chat and see if there's any questions there that are not answered. Okay, Phil, you have a lot of questions. I see that. UA, thank you for addressing those. Yes, is there a benefit complication with respect to coordinating the order, speed, parallelism between the movers? Module moves chosen to be simultaneous in order to cancel out each other's torques. Maybe that's not significant, but maybe it is significant. And that is exactly the type of thing that we would love to consider in the extension to this project. Right now, you're right. Module movements are basically individual decisions, right? You receive the stress token and you head over there. And you don't, the only sort of constraint locally is, will my motion cause a new disconnection in the graph? If not, let's go. That's how it works right now. But yes, the sort of global understanding of what the picture is, what's the big picture of this modular robotic system, and trying to maintain some constrained motion there. Yeah, that is a extension that we're planning. It definitely could be significant. One more note I would like to say here. Right as we were releasing this project, Sakana AI also released a very, very interesting and related project on global topology sensing for modular systems. So they can a module within a larger modular system sense the nature of the structure that it's a part of. I think that there may be some potential for including those global topology sensing ideas for exactly what you're talking about. Um, so yeah, great question. And yes, we're thinking exactly along those lines. Does the method hold if nodes have heterogeneous roles, even if they have the same shape? Another extension. We want to, yeah, exactly, UA. That is something that we want to explore for sure. For example, there may be modules that are power modules, or there may be modules that are compute modules. This gets into an idea that we were recently discussing with a professor at UPenn about fine-grained modular structures. So coarse-grained modular structures, everybody's got a battery, everybody's got a computer, everybody's got motors on board. Um, but what if that's not the case? What if each module in the modular robotic structure is specialized? In that case, you can make a much finer, much smaller modular structure with more modules and more structural integrity, but it becomes a more difficult control challenge, becomes a more difficult algorithmic challenge. So yeah, attacking fine-grained heterogeneous swarms uh, is another next step for this project. There's a lot of this is kind of we're at the base of a tree, and there's many branching paths that we can go down. Okay, I see that you also raised your hand. Go ahead.
Great talk. Thanks for answering my questions to you
Of
both.
course.
Yeah, well, there's many directions this could go. Can you comment on the leap between where you are now, and how far until that next extension? Like, which ones are just that you need more time, and which ones are we need to solve more math? Like we need to invent more algorithms. Where are the gaps?
Right. The maintaining global topological constraints as you reconfigure that we need more math for that. In fact, right now we're deep in the research stage for that. I'm looking into this topic called calculus of sheaves. I'm not 100% sure if it'll apply, but we're still at the stage where we're pursuing leads to try to um, maintain global topological constraints. That's untouched in the research. That has not been done before. Um, and so our immediate next step is the rapid reconfiguration project, which is, okay, rather than homeostatic mechanisms, let's attack the first of those three biological capabilities, morphogenesis. Let's try to create methods so that modules can go from any initial shape to any terminal shape. And we're already hard at work on that. So Stanley is actually leading that effort. He's here in the chat. That's our next step there. There's one more branch to that tree, the fine grained structures thing. I think that sits somewhere in between the two. Um, it's possible that a simple adaptation of the stress sharing mechanism could apply to some fine grained structures. That'll really expand the applicability of this project for sure. Um, yeah, I think so. That's the order. So nearest term, rapid reconfiguration, then extension to fine-grained structures where all the modules are different or have different roles, and then finally, let's try to maintain topological constraints while we're operating. Does stress sharing work for mechanical stress too? Yeah, potentially. Actually, that's a great idea. If a module is feeling mechanical stress, it propagates a stress token, and more modules head over there to try to bolster the structure in that area. I think that's like an immediate additional application that we could apply. So that's why we wanted to target this idea of graph connectivity because it's very general. Like graph connectivity is a mathematical idea, and it can apply to all kinds of things, power, communication, or mechanical stress, like you're saying. Uh, so yeah, definitely. Great questions. Great questions. Any other questions?
Um, yeah,
Yes.
this is a great talk. Yeah, I have some question about like the goal of this project
Hmm.
here we have is that so if correct me if I'm wrong, the way that I understand it is like we have a graph structure and there are some components are broken, but they are still physically there. It's like it's not like the broken piece of the modular robotic is gone missing, so we still have like a chance to reconfigure other parts of the swarm to make the rest of the robotic swarm to be connected. Is
Yes.
it, yeah, I see. So um so this project does not consider about the metabolism step, right? It doesn't consider about like
No.
after we connect and we can clean out the broken parts, something like that. I see.
Yeah. So let's just briefly go back to that.
Hmm.
Yeah. So these three capabilities, morphogenesis,
Mm,
homeostasis, and metabolism, I view them as separate. Ultimately, we want to design systems that have all three, but the way that you do each is going to be different from each other. Why?
mm,
Because morphogenesis is the global reconfiguration of the modular system so that it turns into the desired final configuration while everything is working as intended.
mm,
And so that it can be relatively slow. It can be um, relatively computationally intensive. Sorry, it can be relatively computationally slow and it can be relatively physically slow
mm,
because, it's global morphogenesis. It will always be limited by the actuation speed of the modular system itself. Okay. Homeostasis, on the other hand, needs to be rapid. It is the situation where some damage has disrupted the function of the system in some way. And so, like you getting illness, your immune system will immediately try to correct that, right? Or actually, an even faster example of homeostasis would be um, if you take an ice bath, right? Or if you're in a hot area, you'll sweat immediately. Why? Because
mm,
homeostasis needs to be reached as soon as possible. And so to make homeostasis in modular robotic systems, we have to, it needs to be fast, it needs to be decentralized, it needs to be localized. Um, yeah, sorry, another biological example is when you touch a hot stove, the you immediately pull your hand back. Why? Because the nerve signal doesn't even travel all the way to your brain. It is not a conscious decision to pull your hand back. The nerve signal travels into your spine and is dealt with right there. That's your reflex, right? Homeostatic mechanisms need to be reflexes so that the system can recover as quickly as possible and not sustain further damage. Um, that's the idea there for homeostasis. Metabolism is interesting. It's not necessarily it's a new capability on the engineering side, but not necessarily on the algorithmic side, because as soon as a new module is added, then it's part of the modular system, right? So
mm,
that's there's not too much algorithmic difficulty there, but metabolism is what links the two together and what makes homeostasis sustainable, because homeostasis is just maintenance of function, but you still have this scar tissue. You still have these damaged modules. If you want to
Yes.
get right, if you want to get rid of that damaged module, um, you need to eat. You need to get more new modules into the system.
Okay, excellent. Yeah, that's very clear. Yeah, so this project is mainly focusing on like homeostasis
Correct.
phase. Gotcha, gotcha.
Correct. Now,
Okay.
when we really build these systems, which will
Mm,
be soon, when we build these systems physically, um, metabolism, homeostasis, morphogenesis will apply all three into one system and demonstrate, a fully biological kind of modular system.
mm.
That's the dream.
Excellent,
Not dream,
excellent.
sorry, that's the goal. This it's coming.
That's the goal.
It's coming.
Yes.
Yeah, it's coming.
Okay.
Cool. Thank you, Stanley. Any other questions, guys?
Said there's one in the a chat
Oh,
from
okay,
Gagan.
perfect. Okay, Gagan. So broken parts are disregarded, but can there be a way to repurpose or absorb the broken module into something else? Most definitely, but that is so when we're developing these algorithms, it's a tricky situation. If we are engineering a real system, like if we're really building these modular robotic systems, we want to try to develop capabilities like that for sure. But if we are um, thinking about an algorithm that can apply to as many modular robotic systems as possible, we have to assume as little mechanical capabilities as we can. We have to make the algorithm as general as possible, right? So it can apply to many different modular systems. So with this algorithm, with this work, no, we don't consider reabsorption, like mechanical breakdown of the module. But yeah, most certainly in space systems, we want that. We want cannibalism, right? Or digestion, true digestion, where broken thing is really repurposed and recycled, and that can happen at multiple different levels. Maybe you just harvest the springs or the remaining working solar panels from the thing, or maybe you literally smelt down whatever the material is made of. But those are entire fields of research on their own. But yeah, that's definitely applies to autonomous, self-sustaining, modular robotic systems in space, yeah, they need to have that capability for sure. So thank you for your question. Excellent. So it seems like that is everything. So once again, guys, thank you very much let me just briefly go back to that thank you slide, uh, just in case there's another link, a link that you guys want to take a look at. Okay, so yeah, guys, thanks once again for coming to this Frontiers talk. It was an absolute pleasure to work on this project. Thank you to Yue for sticking with it and pulling this through and getting this preprint out and pushing this ahead. I really appreciate the work from the team. Um, Thank you to the larger Manifold team for supporting this event as well as our research demo days and as well as other sort of outputs that led to this final release for this project. Um, I'm stoked. We're stoked. There's a lot more to do in the future, and you're going to hear a lot more from us very soon. So thank you, everybody. Have a wonderful rest of your day. The video will be up on Monday. Thank you.